So in this section, 4.3, we're going to take everything we know about inverse functions back from Algebra 2 or pre-calculus. We're going to combine it with what we know about the chain rule and implicit differentiation to find the derivatives of even more functions that we haven't learned how to find derivatives of yet. So remember that inverse functions, two functions are inverses if they undo each other. An example of a pair of inverse functions is the squaring function, y equals x squared, and the square root function, y equals square root of x. Because if you take a number and you square it, and then later you take its square root, you get back to the same number you started with as long as your number, the original number is greater than or equal to 0. So a couple of new vocabulary ideas. A function, for example, f of x might equals x squared might contain a point 2, 4. The inverse function, by definition, the domain and range values swap. So the inverse function is going to contain 4, 2. So if one function f contains a, b, then f inverse is going to contain b, a. And we have to know this notation here. We say f inverse. That -1 floating up there in the air is not an example of an exponent. It's part of function notation, and specifically it means the inverse of the original function f. The function that undoes whatever f did. So if f contains a, b, f inverse contains b, a. You can see an example here. I have a function, y equals x squared. We know it contains 2, 4. So the square root of x is going to contain the ordered pair 4, 2. We could use everything we know about derivatives so far and find the derivative of y equals x squared at that point. So I know how to take the derivative of x squared. Oops, that was that last. So the derivative of x squared is 2x. And at the place where x equals 2, the derivative, or the slope of the tangent line, is going to be 4. So if I come down to this other function, y equals square root of x, there's a corresponding point, 4, 2, and I could figure out the derivative of square root of x, and I could find that at 4, 2 on the square root of x function, I have a derivative of 1/4. So the slopes at corresponding points on reciprocal functions, on inverse functions, are reciprocals. And we just did this one example, but we can use calculus and some algebra to prove that this is always going to be true. We're going to show you next how to use it to solve problems on the AP test. Okay, so this is one way to think about it. These words might be more helpful than this formula, these words. So the derivative of f inverse evaluated at f of a, meaning the output of the original function, which is going to be the input to the inverse function at the corresponding point, is equal to the reciprocal of the derivative evaluated at a, the derivative of f evaluated at a. So let's take your handout and fill in these big ideas. So if the function f contains the point a, b, and has slope m at that point, then its inverse function, which is called f inverse of x, that's an f with a -1 up there, but that is not an exponent. It's a part of the function notation, meaning the inverse function. It's going to contain b, a, and have a slope of 1/m. So I'm going to show you how this shows up on the AP test, and what I have written down here, I've never seen it in a textbook, but this is exactly what I do to answer these kinds of questions. So I'm going to teach you my way. If you find somewhere else that actually teaches how to do these problems, feel free to use it. I feel like I had to invent my own because it never really got taught somewhere. So I have a function f. I know f of 3 is 15, f of 6 is 3. I know the derivative of f at 3 and the derivative of f at 6. And I got this new piece of information, which is G is the same as F inverse. So that means F and G are inverse functions. And I've been asked to find G prime of 3. I'm going to use the information from this box, which you should end up knowing by heart. And I'm going to have, I made 2 of these little tables, one for the F function and one for the G function, which I've been told is the same as F inverse. Now I have to ask myself, what did they ask me for? They asked me for G prime of 3. So that's something about the G function. So my answer is going to end up filled in this table. And specifically, G prime means slope. So if I could fill in this box, that's going to give my answer. So I'm going to start with what I know. I've been told that the point on the G function that I care about the slope at is when x is 3. So now I got to figure out how to fill in this big box at the end using just the information I have. So what I start with is the fact that if my inverse function contains b comma a, then my original f function must have contained a comma b. So if this 3 is the x on the inverse function, then 3 must have been the y on the original f function. So I need to look through my list of ordered pairs of the f function and figure out which one has a y value of 3. Well, here I have an input of 6 gives an output of 3, so now I can fill in this x. And I know when x is 6 on the f function, y is 3. So on f inverse, which is g, I know that when x is 3, then y is going to be 6. I still need to figure out the slope of the g function at the place where x equals 3. And I'm going to use that second part here, which is if I could figure out the slope of the f function, I would just find the reciprocal. So can I find the derivative or the slope of f at 6, 3? Well, that's going to be, the input is 6, that's going to be f prime of 6. So if f prime of 6 is negative 2, that means the slope of the f function is negative 2 when x equals 6, which means the slope of the slope of the inverse function at the corresponding point is going to be 1 over negative 2. So final answer, negative 1/2. All right, so I'm going to end this video with this picture. This is a little graphic that's giving you for free the derivatives of the 6 inverse trigonometric functions. At this point, I would typically have shown you a derivation, either using the formal definition of the derivative or something else to prove to you why these derivatives exist. I'm going to do that in a separate video because knowing that math is interesting. I think it's interesting. It's not actually something that's covered on the AP test. So I'm going to make that video optional, but you're going to want to know these 6 derivative formulas by heart. I'm going to start the next video with the same picture, talking about some ways you can remember these rules and what it means that I'm using u in these rules instead of just x's. So optional video on where these rules come from, and then check out the beginning of the next video. We're going to talk about why I have u's and not x's, and we're going to talk about how to use these formulas. We'll practice using these in some released AP style problems.